In this video, we will be learning about calorimetry. Calorimetry. This is a physics lesson, and um, basically, the meaning of calorimetry is I actually don't know the formal definition of it, but uh, sorry, calorimetry. So, okay. So, calorimetry is basically the process of measuring the amount of heat released or absorbed during a chemical reaction. So, this basically involves endothermic and exothermic reactions, which basically means the absorption and the release of heat respectively. So, yeah, as stated here, exothermic releases heat, endothermic absorbs heat. So, yeah, we'll be involving three formulas here. Well, particularly this is the main formula. Q is equal to mcaT, such that Q is the amount of energy. M is the mass, as usual. C is going to be the specific heat, which such that the unit is usually calories over grams times degrees Celsius. But then this is conditional. What do I mean by that? I'm not sure what this is formally called, but say this is temperature. So we have something like this. This bar, we're trying to pertain to water, okay? So this is the latent heat of fusion, and this is the latent heat of vaporization. So basically, regarding water, it starts to melt at 0 degrees Celsius, and it starts to, once it becomes liquid, like as in literal water, it is capable of turning into gas or water vapor by the time it reaches a temperature of 100 degrees Celsius. So in these particular scenarios, if you are in either of those two of the latent heat situations, I believe the formula for specific heat is calories over grams. That's why here it's stated as a fixed value that the latent heat of fusion of water is 80 calories per grams. There's no degree Celsius. I'm not sure about the reason why there is no degree Celsius, just like this and like this. Probably, I'm not saying that this is the right answer. It's probably because there is no change in temperature, I guess, in either of these two. So, yeah. Although, yes, you don't really have to dwell much on that matter. Just know that these are the formulas. This is the unit for specific heat. And adding to that, we also have here the specific heat values for water, ice, and vapor. Although they're the same physically, I mean, they're the same matter, but they're in different physical states. It's important to know that the specific heat can also differ. So, in this simple graph, this is basically the region where the matter is water. This is where it's water vapor, and this is where it's ice. So, water is here. The specific heat is always going to be 1 calories per grams times degrees Celsius. And for ice and water vapor, both extremes, above or below, they have the same value in terms of its specific heat. So it's 0.5, basically half of the specific heat of water, which is 1. So aside from that, you can take the liberty to memorize all of these values. It may come in handy, especially if you're taking any college course, or if you have a high school lesson that tackles heavily on these topics. It's gonna be really helpful, especially if you try to answer word problems and the specific heat of certain mentioned substances are not mentioned. So yeah, good luck with that. I'm hoping that my teacher could also challenge us before the school year ends. Like, you have to memorize all of these values just to get used to college life. Because I know there will be a lot of memorization when we get there. Anyways, so we have here another formula. So the change in temperature, it's basically TF minus TI. Also, I remember from class that in a certain scenario, it's actually like this. It's the opposite. So they're basically in different positions, but the minus sign stays in the middle. It doesn't change position. Also, I'm not sure what that scenario is yet. You might get to it as we answer. Or wait, actually, let's look it out now. Um, okay, I think it's this. Is it? No. Hang on. No, that's thermal expansion. That's gonna be a different topic, a different video. But what do we have here? Ah, yes. This is basically the graph that I was trying to draw a while ago, although in a more simple way. Okay. So spoiler alert, the answers are already here, but we'll be solving them. The solution is more important because without it, the answer is pointless. Okay. Ah, yes. This is what I was emphasizing earlier. So, if it's latent heat of fusion or latent heat of vaporization, either of the two, the unit is only calories over grams, not calories over grams times degrees Celsius. Okay. Ah, yes. Okay, so basically, for the change in temperature, it's basically high minus low. So usually, the higher temperature is TF, this one, but granted that it's actually lower compared to TI, it's you have to um, make the formula, the change in temperature, basically high minus low. So this is a safer formula compared to this. Where do we find this kind of scenario? Um, so example, we have a mug that is full of water, and we put a hot spoon. We dip a hot spoon um, in the water. So the water is cold and the spoon is hot. So uh, of course the heat has to be distributed evenly. And yeah, more on that later. But at least I already raised the topic. I brought it up already. For the third, we have Q gain is equal to Q loss. So that's actually related to the mug and the spoon. So either the spoon or the mug. I believe it's the mug. Whatever is cold will gain energy, and whatever is hot will lose energy, so that thermal equilibrium can be achieved. So yes, let's try to answer number one. Okay, hang on. You can fast forward. Okay, so we have to calculate the energy in calories for 15 pretzels if the temperature is sorry if the rise of the temperature I don't understand this grammatically. Okay, so let's so we're looking for energy. Let's write down the formula again. Q is equal to mcaT. It's usually written like this, basically the temperature, but it was recently advised that it has to be capital T for some reason. Anyways, so we're looking for energy. Q is missing, but I believe we do have the mass. The mass is 150 grams. 15 pretzels. Does that matter? I don't think so. But we do know that for food in general, such as pretzels, the specific heat. Well, no. Please disregard what I said. So 150 grams of water. This could be translated to ml, but it certainly pertains to water. Even if grams isn't usually associated with water normally. So specific heat of water, again, is 1 calories over grams times degrees Celsius. And the change in temperature, the temperature that we have, is 45.3 degrees Celsius. So we got everything that we need. Let's solve. So 150 grams times. Hang on. Before I proceed, which is generic, how do you know that this temperature is not final temperature? Well, as simple as the question is, it's very short. I mean, what else can be the change in temperature? This one. If it's not this, right? So, yeah, we don't really have to overthink in that regard. As much as I still don't understand completely why. But I believe it would be understood eventually. More practice. That's what it takes. So 150 times 45.3. What is the answer? So we have 6,795. And what is our remaining unit? Calories. By the way, energy is measured in calories. At least in this lesson. I believe this is the SI unit for energy, calories. Okay, let's go with number 2. Okay, so you have 500 grams of water. Again, water, so we'll list the specific heat as well as its mass, which is already stated. What else? During experiment, what is the temperature change experienced by the water? Okay, so this time we're given the energy value, which is 2,000 calories. So let's bring out the formula again. Q is equal to mcaT, such that what we're looking for is the change in time. So we can articulate the formula in this particular fashion. And from there, the change in temperature is equal to 2,000 calories over the mass, which is 500 grams, times the specific heat, which is 1 cal over G times degrees Celsius. Okay. You might wonder why I'm still extending the solution when it could already be easily solved. Uh, my teacher has trained his students, to answer it this way, so that, yeah, I do recognize that it's important to be punctual, and the solution isn't supposed to be very sloppy. But yeah, I mean, yeah, I understand that it's important for college, although it's already kind of exaggerated and ridiculous. But anyways, we got the answer. So yeah, what is the temperature change experienced by the water? 4 degrees Celsius. That's the change. So after absorbing 2,000 calories of heat, this is 500 grams of water, by the way. Um, the temperature changed. The temperature change was 4 degrees Celsius. So that's it for number 2. Number 3. Okay, number 3. 550 calories of energy are produced when the temperature of water in a calorimeter is increased by. Okay, so definitely the temperature value is the temperature change. And what we're looking for this time is the mass of the water. But you're also given, it's already implied, since we're told that it's water, the specific heat of water, like literally in liquid form, is 1. If it's ice or vapor, it's 0.5. Remember, again. Okay, let's bring out the formula. Q is equal to, what we're looking for is M, so we can articulate the formula this way. Okay, mass is equal to 550 calories times the specific heat, which is this value, and then 37.6 degrees Celsius. Okay, 550 over basically 1 times 37.6, and we cancel, and yeah, we have 14.62766. I think these two cancel out as well. Okay. You do have grams, so that's what remains. But let's see how the unit grams is articulated so that it's properly understood. So 550 calories over 37.6 calories over grams. And then 550 calories over 1 times grams over 37.6 calories. Okay, makes sense. And that's when the calorie units cancel, and these are divided, and then we have the grams. Therefore, we end up with this. Clear. Okay, number 4 and 5 and 6. Oops. Kindly fast forward, please, to the point where I'm gonna answer. Number 4. When 175 grams of water is heated from 22 degrees Celsius, so I think from this word from, this is definitely not change in temperature. It's more likely the initial temperature. So Ti is 22 degrees Celsius. Calories of energy, 375 calories of energy are produced. So Tf is missing. So this is technically still water. So the specific heat of water is 1 calories over grams times degrees Celsius. So Q is equal to mcaT. We can turn the formula in this way. So Tf minus Ti. Okay, so this is the scenario says that the amount of water is heated. So definitely the temperature of water, the final temperature is expected to be higher. So earlier, our formula for the change in temperature is high minus low. So it's technically safe to say that Tf is higher. So Tf minus Ti, that's our way to go. And yeah, articulate the formula such that we're looking for Tf. How do we do that? So mcTf minus mcTi. mcTf is equal to Q plus mcTi. Tf is equal to Q plus mcTi over mc. So I believe this is the formula for final temperature. It's derived from this original formula, the energy formula. So what is Q? Q is 375 calories. What's the mass? 175 grams. How about the specific heat? 1. How about the initial temperature? 22 degrees Celsius. How about the grams below? Okay, the same thing, as well as the specific heat. Okay, all good. So in the numerator, 375 plus 175 times 1 times 22, that is 4,225. So where do we cancel these? So we have calories in the numerator. And below, it's basically 175. Anything multiplied to 1 is the same number that it is. So calories over degrees Celsius. Okay. So the gram units cancel. Okay, so 4,225 cal over 1 times degrees Celsius over 175 cal. Cancel. 4225 divided by 175 is 24.14286 degrees Celsius. So definitely it rose by 2 degrees Celsius. Roughly 4 degrees. 24, basically 24 minus 22. Okay. That's number 4. How about number 3? What did I get for number 3? Okay, so far so good. Number 2, number 1. Okay. Number 5. So when 27 grams of water absorbs, okay, so this is the mass, 27 grams, 1,500 calories of heat energy. Q is equal to 1,500 cal. Temperature of water was raised to. So instead of the preposition from, it is stated to. So this is definitely final temperature. So Ti then is missing. Another reason why this is not Ti is because following that statement, we're looking for it. So it's definitely not given. So we're still dealing with water. So specific heat of water is 1 calorie over grams times degrees Celsius. Okay, again, articulate the formula this way. So it says absorbs, not release heat energy. So definitely, the final temperature is gonna be higher. So high minus low, TF is here. So it's right. We're looking for Ti, right? So Q is equal to MC TF minus MC TI. MC TI is equal to MC TF minus Q. Ti is equal to MC TF minus Q over MC. Ti is equal to, okay, so what's the mass? Mass is 27 grams. How about the specific heat? 1 calorie over grams and degrees Celsius. How about TF? That's 57.5 degrees Celsius. How about the heat? Or the Q? 1,500 cal. And the mass, 27 grams. Specific heat, like so. Okay, so 27 times 1 times 57.5 is equal to 1,552.5 cal. And then minus 1,500 cal over grams, calories over degrees Celsius. $27. Okay, 52.5 calories times, basically reciprocate that. And we have 1.94445 degrees Celsius. Let me just confirm this in a short while. Okay, yeah. Is this our answer? Okay. Number 6. Pity. 3 questions did not fit in 1 page. Okay, so we're done with water. We're now dealing with a substance called iron, or basically Fe in the periodic table. So the mass is said to be 400 grams. It is plunged into a beaker containing 1 kilogram of water. Okay. How do we do this? sorry, what else do we have? This is already thermal expansion. Sorry. Uh, how do we answer this kind of question? Okay. Yeah, I'm afraid I'm gonna need to make a part 2. I did ask my teacher in advance to um help out on this, but to no avail. There's no reply. Anyways, yeah, we did answer 5 questions. I don't know if I should continue with thermal expansion in the same video. Doesn't feel right. But it doesn't feel right either to just skip this question because I couldn't answer it my own. Anyways, yeah, I'll just end this video. Um, I'll make a part 2 answering this question alone, and another video for thermal expansion and a continuation of combination circuit, which I promised to finish this one. Okay, thanks for watching.